This lesson focuses on the binomial theorem questions that have appeared in the most recent HSC exam papers. I will lead you through the solutions to these questions and will look at them in increasing difficulty. Binomial theorem is commonly tested in the HSC exam, and its application also extends into probability, but we'll look at this in another video. First up, let's look at the multiple choice example from the 2014 HSC. It occurs at question 3 of the multiple choice section and is therefore relatively straightforward in terms of its application of content. The question is asking us to identify the constant term in an expansion that contains two pronumerals to the power of 12. Your reference sheet links to the notation required for a binomial expansion, and so the first thing that we should do is consult the reference sheet. The expansion formula is located at the bottom of page 4 on the right-hand side, and it looks like this. From our classwork, we know that any term in the expansion is the product of the combination of that term, the first term in the expansion with the opposing power, and the current power of the second term in the expansion. Now linking the formula to the question, we can see that our value of n is 12, our first term in our expansion, or our value of a, is 2x, and our second term in our expansion, our value of b, is negative 5 on x cubed. And we need to be very careful of that negative value. As the question is asking us to calculate the constant term, it's requiring us to find this value of k that will give us back a term in the expansion that has no x value on it, meaning that x's power is 0. So using the formula from the reference sheet, we'll find a general term that describes any of the terms in our expansion, and we'll link this to the one where the power of x is equal to 0, and hence find the value of k that we're looking for. So for the general term in our expansion, which we'll call t of k plus 1, we need the product of the combination at that point. The notation used in the reference sheet is to list the values that we have to choose from at the top and the value that we wish to choose underneath in bracket form. It really doesn't matter which notation you use, but if you have a look at how our answers are listed in the multiple choice question, they've matched the notation to the reference sheet, and so we should do the same. As we've been using the combination notation in class though, I'll begin using that and I'll convert it at the end. So our combination is 12, choose k, as k is what we're trying to find. Our a value in our expansion with the opposing power is 2x, and I'll make sure that I put it in brackets as there are two values there, with a power of 12 minus k. And our second term, or our b value, making sure that I include the negative, is negative 5 on x cubed with a power of k. As I need to equate all of my x values to a power of 0, I now need to combine all of the x values in my general term. So I'm going to use my index laws to break apart all of the terms that I see and combine the x values together so that I can equate them. So this gives me the combination out the front, which remains unchanged. I'll have a 2 with a power of 12 minus k multiplied with an x with a power of 12 minus k multiplied with a negative 5 to a power of k, and using my index notation, an x to the power of negative 3 all to the power of k. So So collecting like terms, we have our combination, our constant values, and our values of x. So we have x to the power of 12 minus k times x to the power of negative 3k. And using our index laws, we can simplify that further by collecting the x's together and creating one power. So multiplying the bases means that we'll add the indices, and we'll have 12, and negative k plus negative 3k is negative 4k. So now that we've identified our x value, we can equate it to the power that we're looking for. So our constant term, or our value that's independent of x, occurs when x's value, or power, is equal to 0. And so the next line, I'm just going to consider those x terms. I want that x in my general term that has a power of 12 minus 4k to be equivalent to x when it has a power of 0. And by doing this, it will give me the value of k where the constant term is occurring. So equating the powers, we've got 12 minus 4k should be equal to 0 to give us a constant. And solving the equation in front of us gives us back that k's value is 3. And now that I've identified where my constant term is occurring, I can substitute that value of k back into my formula that I found for my general term and identify what that constant should be. So substituting it in, I will replace k with the value 3. So we have 12c3 times 2 to the power of 12 minus 3 times negative 5 to the power of 3. And our x value, we now know, will have a power of 0, which we see occurs when you substitute 3 in. So that power of 0 gives us a value of 1, and hence the constant is identified by calculating 12c3 times 2 to the power of 9 times negative 5 to the power of 3. So now linking back to our answers, we can see that half of our answers are positive values and half of our answers are negative values. So we need to consider what's happening with this negative 5 when we cube it. We know that any negative value to an odd power will remain negative, and so overall our constant term will be negative when we calculate it. By considering this, we can then match the answer that we found to the answers listed, and so our answer to this question was C. The next binomial theorem question in the 2014 HSC occurred about halfway through the paper at question 12D. They've given us a hint here that they want us to use our techniques from binomial theorem to show that this expansion in front of us is equivalent to 0. So looking at the expansion that they've given us and considering the notation that we've used in class, this expansion here reads NC0 minus NC1 plus NC2 and so on to the last term, where they're identifying that the value we're expanding against is a negative 1, and hence why we have changing symbols, all the way up to NCN. And as the question is asking us to show we need to show every step in this process that links to the binomial theorem and prove that when we do expand it, we will get a value of 0. By considering the expansion that we have in the question, we can see that they are combining the combination with one other term. So our starting point here is just to consider the expansion of a basic binomial and link it to the one that we have in the question. So let's consider the expansion of 1 plus x to the power of n. We know from our classwork that this general expansion will give us the combination for all values of k up to n multiplied by x to the value of k. And we'll continue on for every value of k until we reach the final value of n. Now, linking this general expansion that we've learnt in class to the question that's in front of us, we can see that for all of these values of x, our sign is changing from positive to negative. All of the combinations match, and we also need on the right-hand side here a value of 0. So using the same idea that we used in the previous question, where any negative value raised to an odd power will remain negative, if we let x equal -1, not only will that give us on the right-hand side a value of 0 inside that brackets, but it will also allow us to change the sign for every term in our expansion. So the first one, being a power of 0, will give us back a positive 1. The next one, with a power of 1, being an odd power, will give us back a negative. The third term in our expansion will have a positive power and hence give us back a positive, and this will continue happening until we get to the very last term in our expansion with a power of n. And so simplifying our expression and using the notation listed, we'll obtain the exact expression that we were required to prove. And so we finish the question.